Hello and welcome back to your Machine Learning A to Z course. Are you super excited? Because I am super excited about this tutorial. We're talking about nonlinear support vector regression. This is going to be quite an advanced tutorial, but don't worry, we will break it down, and as per our mission, we'll make the complex simple. So before we start, just wanted to make sure we're on the same page. So this is one of the most advanced tutorials in the support vector series of tutorials. Please make sure that you've completed all the previous tutorials on SVR and SVM and kernels before proceeding with this tutorial, because you'll need all that knowledge to be able to tackle this one. All right, and off we go. Here it is. So imagine you have a data set like this, and you're trying to fit a support vector regression onto this plot. You want to see what kind of trend line is there, or what kind of equation is behind this. How do you model this? What kind of model can we fit to this, a support vector regression model, so that you can predict what the next value is going to be for a new point that is added to the plot. So if you know X, what is going to be Y? Well, you might want to try and fit a linear support vector regression, and it'll look something like this. You'll have these support vectors, but as you can see, like intuitively, you can tell it doesn't fit, right? Like you can tell that something is going on here beyond linear, and like while it might model maybe okay there somewhere at some point, clearly if you get a point with X over here, you're going to get the incorrect value, or if X is over here, you're going to get an incorrect value which doesn't fit. Looks like something else is going on. You might try something like that, then that won't fit as well. That doesn't fit, so it doesn't look like a linear model fits here, and it looks like something more complex is going on. So how do we build a support vector regression that will fit our data here? Well, this is where nonlinear SVR comes in. It's going to be quite interesting because we need to go to a new dimension, and that's why we're going to add this box. It's just for visualization purposes. Like our data hasn't changed, our axes are the same, but just for us, once we're transitioning to a third dimension, to keep track of things, we're going to add this box, and we're going to add these diagonals as well as a point, a red circle in the middle, just so visually we can see what's going on. It'll help us. It's just like a visual aid. It has nothing to do with the algorithm itself. It's for illustrative purposes. So now we're going to actually take this and look at it from a different perspective, at an angle. So at an angle, it looks like this. And that will allow us to build that dimension Z. Now let's get rid of the previous view, and we're going to make a copy of it, because there's going to be quite a lot of things going on, and in order to keep track of everything, we'll have two charts that are developing in parallel. So now on the right, what we're going to do is just as we did previously with support vector machine, and that's why it's important to have seen those tutorials. We're going to add a kernel, and in this case, we're going to add the or a new function to take us into a third dimension. We're going to add the radial basis function, or the RBF. So there we go. That's what it looks like. That's with the RBF. You can see our data vaguely underneath, but here you can see it more clearly. And just as a reminder, the formula for the RBF function is over there. Now, if we project our data into onto this RBF, you'll see how it works. So first of all, the center 0, or this point 0, 0, 0, 0 on X and Y axis projects straight into the very top. And if we discussed this before in the tutorials, if you put 0, 0, 0, L is the distance from the center, you'll get at the very top, you'll get a 1. Now let's see how these other points, the other points in our visualization, will be projected onto the view. So we're going to start with this point over here. So that point will be projected into this point in the Z-axis somewhere here. By the way, some of these things might not be absolutely 100% accurate as I'm drawing them here, but they deliver. Hopefully they deliver the point home. Okay, so now this point will be projected to over here somewhere. Next point over there, and this point, and then the following points will be almost at 0. So all this blue stuff over here, the bottom is very, very close to 0. So it'll be very close to 0. So as you can see, we've been keeping track on the left. We've done all of these points over here. Now the other points, the remaining points, these ones, they're actually, we can't see them, and in order not to clutter things, anything in this quadrant, in this triangle here. We're not going to plot it because it's on the back. It's on the opposite side of this radial basis function or this view. And we're just not going to plot it, but we can just imagine that they are also projecting onto this mountain on the other side. Now, what happens next? Well, next we need to, in these 3 dimensions, we need to run a linear model. So now we're in 3 dimensions. Now we can run a linear model, and a linear model in 3 dimensions is not a line. So in 2 dimensions, it's a straight line. In 3 dimensions, a linear model is a hyperplane. So now if we run a linear model, you'll see that it will, how does it fit our data? It would fit our data something like this. And what do we want from here? So once we fit the hyperplane to our data in these 3 dimensions, what do we want from here? We want to see where does it actually cross, where does it intersect our RBF, our radial basis function. So basically all the surface that we see here, including the floor, this whole surface, where does it intersect? Well, it intersects over across this yellow line. So that's the point of intersect, or the line of intersect. Now, if we get rid of the plane, we're left with this line. And if we project it back down onto the 2 dimensions, the x and y, watch what happens. So we're not going to draw it on this plot, we're going to draw it on this plot. So watch what happens. There we go, that's our 2-dimensional line. So that's our intersect line projected on the 2-dimensional plot. And that effectively is our model. So if we now look at it in the perspective that we started with, you'll see that that is what it looks like. That's the nonlinear SVR. Now, I know you probably have a few questions. Let's try to dig into some of the comments or some of the concepts behind this. So first of all, here we have this 2-dimensional plot. Here is our 3 dimensions. So why is this SVR, right? So where are the support vectors? Well, in a 3-dimensional space, the SVR would run very similarly to how it runs in a 2-dimensional space. Instead of having like a epsilon insensitive tube, we would have an epsilon insensitive space between hyperplanes. So we would add these 2 new hyperplanes. One would be epsilon above, one would be epsilon below. Remember how we had for linear SVR, we had just a tube, but now here we have this space in between them. And so basically what that means is any points that are in between these 2, like the outmost hyperplanes, any points in between them, they won't be considered towards the error for those points will not be considered. What we want to do is we want to minimize the error from this epsilon insensitive space to the remaining points that are outside. And what this looks like over here is that's our bottom hyperplane. That's its projection of it, or that's a projection of the part where it intersects with our radial basis function, and that's the top hyperplane. That's its intersection, or the projection of its intersection. So this line over here is projected into that one, and basically anything in between was the epsilon insensitive space. Now it's become this epsilon sensitive tube, and these are the support vectors. The crucial point here is that this is the outcome. Originally, these hyperplanes are identified or built from this view, from the 3-dimensional view. So that's where these points come in play. So this point is actually underneath. We can't see it. It's over there. And there's also these 2 points that are on the left. So from here, they're built. And then this is just a projection, just to put it into a perspective. So that's why it's still a support vector regression, because we have these points. Now, hopefully that explains why it's a support vector regression. There's just one last thing I wanted to mention. The final thing is that everything we've been talking about here is for illustrative purposes. In reality, the way this works is very similar to how the support vector machine works, what we discussed about the kernel trick, that in reality we don't have to go into a 3rd dimension, do all these projections, and then find our hyperplanes, find this epsilon sensitive space, and then project everything back and get this. It would be too computationally expensive. So what we actually discussed here is a more complex approach. This would be like the full-fledged approach with going into a 3rd dimension, doing the hyperplanes, coming back, getting our end result. That would be like the full Monty in a way. But effectively what happens, or in reality, is that we use the kernel trick. So just like with the support vector machine, we don't have to go into a third dimension. Everything happens in the same space simply by how we use the kernel trick. Now, we won't dive into more detail on that. I'll let you think about that in your own time on how the kernel trick would be used here, because simply it's a easier concept than what we discussed. By looking at the example of the kernel trick in the SVM, we can extrapolate how that would work or how that would benefit us here as well. But in a nutshell, this is what the nonlinear support vector regression is all about. And the best part is, of course, the result, that it allows us to model nonlinear relationships like this and get insights from our data. I hope you enjoyed this tutorial. This was quite an advanced concept, so congratulations on making it to the end. And I look forward to seeing you on the future tutorials in the course. And until then, happy analyzing.